I'm sure, but we only have 20 minutes. Okay. All right. We're really going to have class now. Okay, so we're going to talk about a couple things today. Really, we're going to focus on the collision model, and we're going to focus on some of the things that influence K. So, we'll kind of title this, What Influences K? And we'll talk about a couple of different things. But as you perhaps saw in the lab, when you calculated K, if you didn't calculate K right, that was definitely going to influence your prediction of how long it took. And so there's some various things that could influence K, and we're going to talk about what those things are. As your book talks about K, one of the things that they mention in your book, which I will just mention because you should have seen this and you probably have, is what they call the transition state model. Your book does not talk about any of the mathematics related to the transition state model and how they use it to calculate K, nor will we. But the idea of the transition state model is simply being able to read an energy diagram and understanding that. So if this is potential energy, we've done this before, and this is the reaction, we know, like if this represents the energy of the reactants, and let's say it was an exothermic process, so then this would represent the energy of the products, and we've labeled all sorts of stuff on here, like this energy here is what in red? Yeah, this is the activation energy, super. But the idea is, with the transition state models, they do calculations that when these reactants collide with each other, at the moment of collision, the bonds within the reactants start to weaken, and the new bonds start to form, and so you get right at the top of this curve what they call an activated complex. And so let me give you sort of an actual reaction so that you have sort of an idea. So let's say we were looking at the reaction of 2BrNO breaks down into 2NO and bromine. And so let's write it. It's an exothermic reaction. So here's energy, here's the 2BrNO. Their potential energy associated with that. A little activation energy, they fall apart, they break into products. So here's our 2NO and our bromine. But up at the top, when these two BrNOs collide with each other, perhaps they form an activated complex. Here's a BrNO, where they start to form a bond with another BrNO. And so some of the bonds start to weaken, like these bonds right here start to weaken that I highlighted in yellow. And then we've got some bonds starting to form. And so this is the activated complex where we have some of that bonds weakening that have to break, new bonds starting to form but are not completely formed. And that's the activated complex. And then they continue, if there's enough energy, the bonds continue to break, the new bonds completely form, and then it falls apart into products. And in this case, more energy was given off than was taken in to break the bonds. So that's the idea. And then with a catalyst, we always say, oh, a catalyst lowers the activation energy. It provides a lower activation energy pathway. Well, how it does that essentially is there is a new activated complex when you have a catalyst. Because the catalyst is pretty much part of that activated complex, it's sort of stuck in the middle of that activated complex, kind of facilitating them getting the right orientation. So what we end up with is this new activated complex, but it doesn't take as much energy to get there, which is why it has a lower energy pathway. So there's a new new activated complex with the catalyst. How about that? That might make more sense. So that's sort of the idea, is there's a different activated complex when you get a catalyst involved, and it happens to take place at a lower energy. So they've done a bunch of mathematics with that and used that mathematics to help explain how they arrive at K mathematically without doing that particular lab that you did. What we're going to look at in a little bit more detail, though, is what they call the collision model. Okay, that pen just changed colors midstream. That was so weird.
Aliens.
Like I started blue, it ended up black. So the collision model, we've already mentioned some of the components, but this is where we're going to get to something called the Arrhenius Equation, which is going to help us to figure out how K changes. And so as we look at the collision model basically talks about the fact that the reaction rate depends on three things, and we've mentioned these three things, but we're going to talk about them in more detail. You know, we said, hey, you know, molecules have to hit hard enough and often enough and in the right way. That's essentially what we're talking about here. So reaction rate depends on these three things. The first one is what they call collision frequency. That's called Z, and it's essentially the number of collisions that occur in a certain amount of time. You know, we said they have to hit often enough. So the higher the collision frequency you have, the more often they're hitting, the more likely they are to react. That's going to affect your rate. So that's the first thing. The second thing we have is the fraction of the molecules with enough E sub A. E sub A is that activation energy. And that's designated F for fraction. Yeah, I didn't come up with these. This is what they call it. F for fraction. And so I'm going to refer to you something that you are familiar with as we talk about F. And that's our good friend, the Maxwell-Boltzmann distribution. So we have this graph where this is, say, the number of molecules versus kinetic energy, their speed, essentially. And we know, like, the graph might look like this, say at 25 degrees Celsius. And if it's at a higher temperature, it starts to spread out. So let's say this is 45 degrees Celsius. So Maxwell-Boltzmann, we've seen this like 3 different times now. The reason that this applies is that if we're thinking about activation energy, let's say that they're hitting hard enough, they have enough activation energy if the amount of kinetic energy they have reaches this level. So we'll call that E sub A. So if that's E sub A, you can see that at 25 degrees, there's just this little tiny amount of molecules that have enough energy that will literally hit hard enough for bonds to break and new bonds to form. But you raise the temperature, and now you've affected the fraction of the molecules with enough E sub A, because now at 45 degrees, we've got, oh, I was meant to use a different color. We have a much larger fraction of our molecules. So obviously temperature is going to affect the fraction of the molecules that have enough activation energy. All right, so that's number 2. And then we have number 3. So number 3 is called the Steric Factor. And it's designated P. And what the Steric Factor is really about is it's about orientation, that they have to hit right. So this is essentially the fraction of molecules with, I'll say, good orientation. So in our example of that BRNO breaking apart into bromine and nitrogen monoxide molecules, you know, there may be some good orientations. So for example, let's say you have a BRNO molecule and it happens to bump into another BRNO molecule. Let's say they're coming at each other this way. Well, the bromines need to bond together, and so these two will end up bumping in and hitting each other and forming a bromine molecule, and these bonds here are going to break, and so we end up with 2 NO molecules, and the reaction happens. It had a good orientation. It hit each other in the right way that those bonds could break and new bonds could form. But if instead we had, say, a BRNO molecule coming at another BRNO molecule like this, where the oxygens bump into each other, well, that one might result in no reaction because they weren't hitting in the right way that the bonds could break and the new bonds could form. So those would have a poor steric factor. The trouble with all of these is they really aren't very measurable. Like, you know, some of these are conceptual, and some of these they have good ways to measure. Others, like the steric factor, tend to be more calculated numbers. And so we're not going to, you know, you're never going to get, oh, here's your P factor. It's a more conceptual number that they do put numbers to, but we're going to change this. These are kind of the concepts behind where K comes from. So here's how K develops, our rate law constant. K, what they say K is equal to is when you take, each one of those, by the way, have numbers. The fraction, the collision frequency, they give them numbers. They can calculate numbers for these things. And they say, hey, the rate law constant is a result of multiplying all of those together. The steric factor times the collision frequency times the fraction of the molecules with good activation energy. And then they do a little bit of mathematical manipulation. Because steric factor especially is hard to measure, these two kind of get tied together. So you'll see this in your book. They get tied together and they call P times ZA, which is known as the frequency factor. So it has to do with collisions combined with how they end up hitting each other in the right way. So they'll combine it together. And then F, they mathematically have found that F is actually equal to E, like natural log E, is equal to negative E sub A over RT. So the fraction of molecules that have enough activation energy is related to temperature, which it should be. It's also related to its activation energy, because if it has a super high activation energy, it is going to be more difficult for it to achieve that activation energy. So that's sort of the idea. So taking a look at this, let's get a different color. Here's my question to you. If E sub A is high, so if your activation energy is really big, what happens to your frequency factor? If this is a big number, it goes down. So your frequency factor will lower. And of course, it's a negative exponent, so we have to consider that, right? So if this becomes a bigger number, the fraction with enough activation energy is going to decrease because that activation energy is really high. What if the temperature goes up? That's supposed to be an arrow. Okay. All right, well, it's an arrow on my screen. Pretend that's an arrow. It might even catch up. Please don't stop working. Okay, there it is. Whew. All right, if the temperature goes up, what happens to the fraction? It goes up. Yeah, that becomes, I mean, we could probably reason that through better than looking at the math, right? Because it's in the denominator of a negative exponent, which just makes that fun to think about. But yeah, so if the temperature goes up, then our fraction with enough activation energy will also go up, which definitely corresponds to what we see in the Maxwell-Boltzmann distribution, and so that makes good sense. All right, so the Arrhenius equation. The Arrhenius equation in its simple form, which we'll never use the simple form, but here's the simple form, is just putting those things together that I just said. That K is equal to this frequency factor times E to the negative E sub A over RT. The trouble is A is sort of this nebulous number that we would need to be given, and so this is not the form we're going to use for the Arrhenius equation. So we're going to turn this into a form more similar to the Clausius-Clapeyron equation in just a moment. So first thing we're going to do is we're going to take the natural log of both sides because we've got, you know, that little e in there, so that will be helpful. So if we take the natural log of both sides, we end up with the natural log of the rate law constant is equal to the natural log of A minus E sub A over RT, which we're going to just rearrange to make it the equation of a line. So natural log K is equal to, I'm just, oops, got a little carried away there. Just rearranging this to, come on, eraser. There we go. I feel like everything is in slow motion. Is equal to negative E sub A over R. Now, by the way, which R do you think you're using here? I've just heard them both. What units do you think activation energy are in? Joules. So which R do you think you're going to use? The 8.31 version, because that's the joules version. So keep that in mind. Anyway, negative E sub A over R times 1 over T plus natural log A. So that's my Y equals... Ooh, what is the temperature got to be? Kelvin, because the 8.314 is joules per mole Kelvin. Yeah. So this is Y equals mx plus b. So a way that they could find A, and like I said, they find some of these things mathematically, is if you make that the equation of the line, and you graph the natural log of the rate law constant versus the inverse of temperature, you'll get a line. How do they find what A is? If you've got this line, how do you find A? It's the y-intercept, right? Because this is B, this natural log of A, so you can find A through that y-intercept. But this has a slope of negative E sub A over R. You know, sometimes people wonder, how do they find activation energy? You know, like, well, how do you literally find it? Well, we've done labs, but we're not doing it this year, but I've done labs in here where you literally do something just like you did with the iodine. I mean, you guys found iodine's rate law constant at room temperature. Repeat that experiment and find the rate law constant when you made all your solutions cold. Repeat it when you made all the solutions hot. You will get a different K each time. And then graph it. Graph the natural log of the K you find versus the inverse of temperature, and you'll get a line. And if you get that line, you can use that line because its slope is negative activation energy over R. You can use that line to find the activation energy. It's just a really long lab because you've got to repeat that one at so many temperatures. But it's one that we've done, and it's not a super hard lab to do. So it's a way that you can find the activation energy. You know, sometimes we're just like, we draw a line, and we're like, oh, this is the activation energy. That's how you find it. See how the rate law constant changes with temperature. But that's not the equation that's going to be most helpful to us. We're going to change that equation just like we did back when we were talking about partial pressures and how they change with temperature. So we're going to do that same mathematical operation. All right, so we are going to take this equation right here, and we're going to assume we're doing it at temperature 1 and temperature 2, so we get rate law constant 1 and rate law constant 2. So here we go. So let's say we have, here is the natural log of rate law constant 2 is equal to the natural log of whatever I just wrote. Oh, go away. There we go. Natural log of, waiting for my, see why these videos are so professional all the time? Natural log of A minus E sub A over R, and we're going to call this temperature 2 because I called that rate law constant 2. We're then going to subtract it from doing the same thing, but we'll call it rate law constant 1, and we'll use temperature 1 in this case. And if you subtract those from each other, what you end up with is natural log K2 minus natural log K1 is equal to the natural log A's disappear because I subtracted one from the other. And then a little rearranging on my part here. Negative E sub A over R, 1 over T2 minus 1 over T1. Yes, I subtracted and then rearranged. And rearrange one more time, and you get natural log of K2 over K1 I'm distributing this negative through, so it becomes positive. E sub A over R, 1 over T1 minus 1 over T2. This is the version of the Arrhenius equation. That was a little too many lines in there. That you're going to tend to want to use. It's just like that Clausius-Clapeyron equation with partial pressures, except this is, if you know K at one temperature, for example, you just did that the iodination of acetone lab, you found some K. If you wanted to say, hey, what would K be if I chilled everything, if I did it at 5 degrees Celsius, then you could know K1 and T1 change to a new temperature. Of course, these temperatures have to be in Kelvin, and you can then find what K would be at that temperature. So it's a super handy one there. If you know K at one temperature, you can find K at another, and then, you know, calculate how it affects the rate. Scott?
Why did you circle that negative sign? What happened with it?
I distributed that negative. That's why, notice these guys are switched. This used to be T2 minus T1, and now it's T1 minus T2. But, you know, just like in the Clausius-Clapeyron, this is how I remember it, you know, whatever K2 is here, T2 is here. I guess we're over at 8:25. I didn't pay attention. But that was the end, so good job. Homework is on the board, or if you're watching this, you already did it. Stop.